네, 올해 KGS 어워드 렉처 행사를 진행을 하도록 하겠습니다. 먼저 그 KGS 어워드 렉처러로 선정되신 선정자분에 대한 소개를 드리도록 하겠습니다. 선정자분이 외국분인 관계로 영어로 소개를 준비를 하였습니다. 네. I would like to introduce the KGS Award Lecturer this year, 2022. This KGS Award is the most prestigious award bestowed by Korean Geotechnical Society to renowned experts in geotechnical engineering. This award started since 2011, and there are only 11 recipients, including Dr. Susan Lacasse, Leo Taylor, Ken Stokke, Richard Fino, Carlos Santamarina, and the last awardee was Professor Youssef Hashishi. Every year, the award committee of the KGS decides the recipient very carefully with sincere respect. The KGS award this year is bestowed to Professor K.Jian Shou, the distinguished professor of the Department of Civil Engineering, National Chungsin University, Taiwan. 네, 올해는 타이완, 대만의 국립중싱대학교의 K.Jian Shou 교수님께 어워드 렉처러로 선정되셨습니다. Professor Shou has published more than 200 papers on a variety of topics, including rock mechanics, engineering geology, and trenchless technologies. He is the elected vice president of ISSMG from this year for the next 4 years. He serves as the editor of international journals such as Tunneling and Underground Space Technology, ASCE Journal of Pipeline System Engineering and Practice. 여러 가지 분야에 대해서 연구를 하고 계시고 특히 올해부터 세계지방공학회 부회장으로 선출되셨습니다. 지금 현재로는 터널링 언더그라운드 스페이스 테크놀로지하고 ASC 저널의 에디터로 활동하고 계십니다. Let's welcome Professor Shou with big applause. Professor Shou, can you hear me? And would you like to say hello to our members?
Okay. Hello, everyone. First of all, I would like to express my appreciation to Mr. Chairman and also Professor Kwon for your detailed and very kind introduction. And I would like to thank you. I would like to say it is my honor to be elected as the KGS Award lecturer, and my pleasure to deliver my presentation on this special occasion, 2022 KGS Spring Convention. Thank you.
Thank you. 그 원활한 진행을 위해서 렉처 비디오를 보내주셨습니다. 그래서 렉처 비디오를 먼저 시청하시겠습니다.
Good morning, everyone. It's my honor to attend this KGS World Lecture, and it is my pleasure to deliver my presentation on this extraordinary event, KGS Spring Convention. I hope that we can physically join together either in Sydney in early May or in Seoul or in Taipei very soon. Okay. As you can see, the title of my presentation today is Advances of Trenches Technology for Underground Infrastructures. I'm going to talk about the development of these technologies and also share with you some of the research progress we have done for the past few years. Okay. I'm going to deliver my presentation roughly according to the structure of my paper. I will talk about the development of TT first, and then I will talk about the key issues in pipe checking, one of the new installation method, and also the key issue in CIPP1 method for the rehabilitation. Okay, and what is the trenches technology? Trenches technology is also called no-dig. It is commonly accepted that it is a method that we could use to install or rehab or repair the underground utilities. And by lack of need for digging a continuous trench. Okay, this picture is very famous and commonly used in the textbook. This image shows the situation in New York City. You can see that underground pipelines is very complicated and it's almost impossible to do the new installation and the rehab. Okay, this picture shows the status, shows you some ideas about the potential impact of the open cut. Okay, the potential problems can be summarized as those five major problems: the traffic congestion, street pavement damage, and also the cost of surface restoration, and also the social impact, especially the direct indirect business losses. So in some countries, the contractors are required to compensate the business affected by the construction. And also, one last thing is about the CO2 emission. I think some of the country also request the contractors to pay the so-called CO2 tax. You have to pay. That's why the trench technology is more and more demanding and is more common, more and more common in the underground construction practices. So these illustrations shows the comparison between the open cut and trenches excavation and trenches method. You can see the third one shows the open cut method to do the new installation. You can see the impact to the traffic is significant. But for the trenches technology, trenches method, the only excavation we have to do is to excavate the lunge shaft and rival shaft. So you can see the impact to the traffic is significantly reduced. So according to the ISTT, International Society for Trenches Technology, the method can be categorized to three different types, can be classified to three categories: inspection, new installation, and rehabilitation. Due to the development of new technologies, especially the sensing technology, so the inspection is more and more advanced. We have options for better application. For the new installation, could be I think for these methods are more familiar for us, for geotechnical engineers, so including directional drilling, pipe jacking, microcurrent, etc. For the rehabilitation, these methods are more and more common in different countries, in different areas. However, the rehabilitation can be divided to three sections: renovation, replacement, and repairs. So there are new technologies, new method we can apply as well. If you want to go and to understand the details, you can check the www.istt.com to have more details. Also, we develop new chart and descriptions. You can have more ideas about these technologies. For the inspection, I think maybe 10 years ago, we only know the CCTV can be used to inspect the condition of existing aged pipelines. But you can see more and more methods is implemented or integrated for better detection. So we can detect the leaking, the location of leaking. Also, we can monitor the gas, the flow condition, and even for the virus, we could use the biosensor to detect the COVID-19 condition. Okay, So for the new installation, I think the most commonly method could be the HDD, horizontal directional drilling. We can use the machine to drill a pilot hole, and we use the reamer to enlarge the hole before we pour the final pipe string into the hole. For this technology, I think the size can be bigger and bigger. So the size of the diameter can be up to around 1,400 millimeter in diameter. And the world record length of pipe jacking is 5.2 kilometer. This case is in Hong Kong. It's a gas pipeline under the sea from the New Territory to the Hong Kong airport. So you can see the HDD is more and more developed and compete with pipe jacking, can somehow replace some project commonly use the pipe jacking. Microtunneling, you can see we have a semi-shear machine. We can dig a hole, and the pipe string is behind the pipe jacking machine, and the jacking system is inside the line shaft and behind the pipe string. Okay, these pipe jacking technology is commonly used in different fields, and the record of this pipe jacking, the world record of the length is up to about 1.2 kilometer. It's a project in Ohio, US. Diameter is 1,500 millimeter. Okay, for rehab, it is used to restore the integrity of the damaged pipeline and extend their operational life. As I said, there are three subsections, subcategories: renovation, replacement, and repair. Repair is commonly used to fix the problem in a local damaged area. For a replacement, we destroy the H pipe and replace by a new pipe. And for renovation, we try to integrate or we properly incorporate and maybe we could use some of the performance of each pipe. So this is replacement. This is called pipe bursting. We use the bursting head to destroy the existing pipe, and the pipe string is behind the bursting head. This is a pipe splitting. This is a pipe split head we use to destroy the H pipe and the new pipe strings behind the splitting head. Renovation, we can have a liner, different type of liner we can install into the H pipe. CIPP could be the most commonly used rehab method in the world. We place the inversely folded liner into the H pipe, and we cure the pipe by heat or light to cure the liner and become the new pipe with structural performance. So, for the trenching technology, they are more and more commonly used in different fields. For example, for the offshore wind turbine field, you can see we install the power cable. However, we have to install the receiving facility onshore. So this cable must be placed on the ground. So HDD are commonly used. It's a kind of very demanding method in the world now. Okay, and also for the H pipeline inspection and rehab, that's very demanding now. And also for the new methods, they are more and more commonly developed by integrating different methods. For example, we have a micro-tunneling machine, but we add like a pipe thruster to provide more thrusting force, more jacking force can be provided by the thruster. And also this is kind of, we call it assisted ramming boring. When we use the pipe jacking, we could use the rammer to provide the pneumatic ramming force to make the, it's a combination of a jacking force and ramming force. So this is also a hybrid method. We call it hybrid method. Okay, let's move on to the second part. It's about the key issues in pipe jacking. If you like, you can check the details in the papers. As we know that the exploration of geologic condition before the project is sometimes difficult due to the traffic and the residential and other factors. However, the uncertainties of the geologic condition could induce difficulties during the construction. Okay. I'd like to use this case. This is as an example. This case is a sewer pipeline in the Taichung Science Park. It's 21-kilometer long sewer pipeline. And the formation along this alignment is a gravel formation with a large diameter of gravel. So this large diameter gravel caused a lot of problem. These gravel composed of quartzite. It's very hard and aggressive for the cutter head and also the drilling machine. Okay, you can see the excessive abrasion for this cutter, and also due to the collapse in the annular space, the gravel caused damage to the concrete pipeline, and also the concrete pipe also damage to the connectors. So what we are trying to do is to collect the sample from the shaft and do some sieving test to understand the size distribution and the probability of the large size gravel we could encounter during the driving operation. So this is this picture shows the sieving test we did in the field. And also we did some analysis of geometry to calibrate the sizes. You can see that this is the penetration of the soil mass, and penetration length of the large particle actually is smaller than its diameter. So we did some analysis and found that we should adjust to about 93% of the sizes. The model we applied is called a transitional probability statistical model. We used the T-Prox as a commercial software we can use, and the theoretical basis behind this is so-called the transitional probability. Transitional probabilities is that the event occurred at the location X plus H actually is based on the probability of event occurred at the location X. So this is a special correlation of the probability of the event. So this illustration shows the sample we collected from the line shaft and rival shaft at different depths. We obtained the gradation curve, and then we divide the gradation to 3 different ranges: below 20 millimeter, between 20 to 200 millimeter, and the larger than 200 millimeter. So we assigned the size in different regions and with different colors. This is the model we obtained by using the software. Different color represent different sizes. So then we can obtain the size distribution along the alignment or line specific cross sections. And we try to use the case to calibrate our model and then to do some prediction to see whether this model is applicable or not. So this is the advancing rate. We try to correlate the size distribution along the alignment with the advancing rate of the pipe operation. So this is the size distribution along the alignment. This is the advancing rate in section A2 to A3. And short summary is that these T-plots are used to do the prediction of the geologic condition, and the trend in material chain and the landing rate have a reasonably good correlation. However, more detailed analysis suggested. However, this study provides a new way to do the prediction for the geologic condition. Then for the second topic is about the behavior of overcut and stop. As we know that overcut is commonly used to reduce the resistance of friction during the operation. However, improper overcut could induce collateral subsidence on the surface and also a sticking condition. Okay. In this study, the numerical method was used, and the condition numerical property in the Taichung area were used for the analysis. These figures shows the measures we used for the analysis. Left-hand side is the straight line pipe jacking case. The right-hand side is the curved pipe jacking case. Okay, you can see the number of elements. For the curved pipe jacking case, it's about 1.5 times more than the one. You can see this 1.5. It's about 50% more. And the pipe jacking simulated by the numerical steps. Remove the soil, push the pipe to the specific location, and then we equilibrate the domain to obtain the new condition of stresses and displacement. Okay. So for the overcut and the sticking, I would like to use this figure to show you. For the overcut, for the straight line pipe jacking, we consider the overcut on the upper half of the peripheral area, and then the sticking is at this location. And for the curved pipe jacking, there are two conditions of overcut. It's 135 degree of overcut or 180 degree of overcut. Because this curved pipe jacking, so this is asymmetric. And for the sticking, there are different scenarios. Could be the inner side of a curved pipe jacking, or could be outer side of the curve, and also could be on the upper upper part, also could in the lower part. Okay, so a different condition, different scenarios. Okay, and for the sticking, two types of sticking with high resistance, so up to friction coefficient up to 0.5 to 3, and the second condition is that the totally stop, the friction coefficient is up to the infinity. So we consider the different types of sticking, and the results shows that the stress state are quite different at the inner side and outer side of the pipe. And also for the sticking with high resistance, the stresses at the inner side are higher than that at the outer side. You can see the comparison between the case with different friction coefficient, 0.235 and to the infinity, it's quite different, and also inner side and outer side are quite different. So this is the Miser stress distribution along the inner side, outer side of the cross section. Okay, this is the concrete surface of the concrete pipe. You can see this is the case without the overcut. This is the case with the overcut. You can see the distribution is quite different. In other words, the behavior is strongly influenced by the overcut. Okay, so the results suggest that the stresses increases for the friction coefficient increase, and the case of scarp with overcut, the impact is more serious. Okay. For the curved pipe jacking case, we consider the scenario in a similar way. However, we consider the skin at 3 different locations: front, middle, and tail, and also up and lower, and also inner side and outer side of the curve. Okay, so these figures show the results, the stress distribution from the inner side and outer side of the pipe with stuck at outside of the curve, outer side of the curve. So this the case which is stuck at the inner side of curve, inner side of the curve, inner side of the pipe, outer side of the pipe. Okay, so this is the compression with the stuck at a different location, stuck at the lower outer side, stuck at lower outer side, but it's the inner side, outer side of the concrete pipe. So so this is distribution. See, this is, I think this is a comparison between you see this is stuck at upper half space, outer side with overcut, but stuck in the inner side of the curve. So you see the behavior is kind of complicated, but it's quite different. Okay. Again, very summary, proper overcut can help to reduce resistance during pipe jacking. However, we must be careful. In case of the stock, stress at the section overcut are much higher than those without the overcut. So in other words, impact of overcut is more serious for the case with overcut. So so the results also suggest that backfill could be a solution to avoid this condition, because backfill can prevent the collapse, can prevent the stock. Okay, and also by the comparison, we can see that the case for the friction coefficient of 0.523 is better than the case with friction coefficient to the infinity. This finding also suggests that lubrication is essential, could be very helpful to avoid the stoppage of the pipe jacking, and also helpful to avoid the shortage of pipe jacking force. Okay, for the jacking force estimation, as we know that we have different empirical formula that can help us to estimate the jacking force. The jacking force mainly composed of two major components. The one component is considered the resistance at the cutter head. The second part could be the resistance from the surface of the jacking machine and pipe strings. Although they have some adjustment due to based on different the databases of real critical cases, and also some of the formula are classified to different soil conditions, different soil types. Okay, this study tried to use a different idea, a different method to estimate the jacking force. We call it displacement control method, because in numerical model, we could assign a specific displacement. And then we can obtain the stress at the cross-section of pipe. In this way, then we can integrate the stresses in the cross-section to obtain the jacking force. So this idea provides alternative to estimate the jacking force. So you can see this is a mesh we applied. So this is the cross-section we plan to estimate the jacking force. We assign the displacement to let this cross-section be pushed from outside of the soil mass to right at the surface, right at the boundary of the soil mass. In this way, we can integrate the stresses at the cross-section. You can see this is the stress distribution at the cross-section, and then we can integrate the stress to obtain the jacking forces. So we consider two cases, the real cases, and with a different driving distance and different sizes, and we consider different contact conditions. As you remember that we usually have overcut, so the condition is not real for all contact. Always have half or 1/3 of contact. So this is results. This is case one. You can see we did some comparison between the jacking force estimated by empirical formula from Japanese GMTA and from the US Kim-Stelling formula. You can see that the empirical formula always overestimate the jacking force at the final stage of the jacking pipe jacking operation. However, our numerical method provide a better estimation, especially at the end. Okay. For the second case, you can see the green line represent the regression of the real case. The red line is from the numerical modeling. You can see the estimation is even closer to the real case. So this idea provide an alternative to estimate the jacking force. So other continuing challenges for pipe jacking operation, including larger diameter, longer distance, difficult geology conditions, sharply curved alignment, etc. And nowadays also we could consider the impact to the environment, such as the vibration to the environment. So there's more issues need to be investigated or studied. For the key issues in CIPP, similarly, we have two papers you could check to see the details of the presentation I give today. Similarly, we did the analysis by Abacus. We used C3D8R for the soil mass, for soil in the pipe, in the liner. And also we applied the C3D8I for the interface. And these are the measures we apply for the straight line pipe rehab by CIPP. This is a curved pipe rehab by CIPP. This is a detailed mesh for the location where the cavity is located. You can see we consider different, we could remove the element to simulate the different scenarios of erosion. Okay, the properties are collected either by the lab testing or from the handbook or the standard. So here I would like to point out, before we did the parametric study, we used the lab testing on the aluminum pipe with a cavity, and we used the testing results to calibrate our model before we apply for the parametric study. So we consider the different diameter pipe, wall thickness of pipe, and also the soil depth, and different alignment, straight line alignment, curve alignment for our parametric study. So these figures shows the comparisons of the stress distribution with a different depth of corrosion. You see, this will remove one layer. The cavity is shallow, and this is the deepest corrosion. You can see the stress distribution are quite different. Okay, and also these figures shows the comparison between the cases with different internal pressure. You can see this is the case with a high risk internal pressure. This case is without the internal pressure. You can see that the internal pressure is also very important for the stress distribution for the pipe with the cavities. These two figures shows the comparison of stress distribution for the cases with different size of the cavity. This is the case with diameter of 10 centimeter, this case for 5 centimeter. Okay, and these two figures shows that stress distribution before and after the CIP liner was installed. You can also, for these two cases, we apply the internal pressure to consider worst scenarios. So you can see the CIPP liner could significantly reduce the stress, especially at the cavity. Okay, the results and the comparison shows that stress distribution displacement due to the damage are more serious for the case with large diameter, with higher internal pressure and surface loading, etc. And this is the case with and without surface loading, corrosion, different condition of corrosion. So results reveal that displacement mainly controlled by surface loading. Okay, and displacement more significant as pipe is deeper in the soil. So, however, displacement can be reduced slightly when the internal pressure increases. It's very interesting. However, the installation of a CIPP liner can be reduced, can significantly reduce the stress concentration. Okay, this is the analysis, the results of the analysis of a curve case. Okay, brief summary. For the curve case, you can see that results shows that the stress concentration is influenced by the internal pressure. And interesting things, the impact is more significant for a case with damage at the inner side of the curve. Also, more significant for the case with surface loading. Okay, and the CIPP can reduce the stress concentration. And also, the result shows that the change of the stress is insignificant for the case of smaller Young's modulus. However, stress can be reduced if the liner has a larger Young's modulus. Okay, this is a comparison of a case with a cavity at the top of the pipe and the side wall of the pipe. And these two figures shows that the CIPP liner can reduce the stresses. However, the difference between the liner with thickness of 5 millimeter are not much difference from the case with liner of the thickness of the thickness of liner is 10 millimeter. So in other words, 5 millimeter of thickness could be enough for the rehab. So this results also suggest that we need to do some design analysis before we assign the thickness of the liner. Okay, so the continuing challenges. This picture shows the real situation for the curve CIPP rehabilitation. You can see some wrinkles because of the curve alignment, there are some wrinkles. For the case with wrinkles, the interface property, the backfill, and also the mechanical property of the liner itself could affect the performance of the rehab pipeline. So more details are necessary to be investigated before we do the design or set up the related standard or code. This picture shows the damage of the sewer pipeline. The left-hand side is a disengaged connector, and right-hand side is damage to the. This is disengaged. It's not disengaged, but also damaged at the connector. These two conditions also could be rehabbed by the CIPP. So their behavior also need to be investigated in more details. You can see we did some lab testing, full-scale lab testing for the case of pipe connector, disengaged connector rehab by the CIPP, and also we did some parametric study with different scenarios in order to have a better idea of the control factors and also the performance of the rehab disconnected connectors. So a brief summary from the above presentation, you can see that for the transit technologies, we have more and more development and new methods that need to be investigated in more details, especially for the key issues for the performance. And these studies could be help for better design and also for development of the code or standard. Thank you for your attention. I think that's about it. You could reach me if you have any question. Thank you very much.
Thank you. Thank you very much for your inspiring talk. Professor Shaw agreed to gladly have like a short Q&A time, so we can take maybe one question from floor. 혹시 간단하게 질문이 있으신 분은 해주시면 되겠습니다. 네, 마이크 혹시. 네.
I want to make sure the sound. Do you hear me?
Professor Kwon, I couldn't hear. Could you please?
조금 더 크게 얘기하시면 될 것 같습니다. 네.
Do you hear me right now?
Yes, please.
Okay, thank you for the presentation. My name is Jin Eung-do from Gyeongsang National University. You told us that this trenchless technology can be classified into three groups like inspection and new installation and rehabilitation. So I am interested in the rehabilitation. So because, for example, like contaminant emission from the pipeline corrosion is very important or serious problem in geotechnical engineering. So you say that the CIPP method is most common or famous method, but I am thinking more, for example, like we have several scenarios. For example, we have water pipeline, we have sewer pipeline, even we have utility pipeline. So when we apply CIPP, is there any difference between them? Could you tell us more?
I'm trying to show you one of the slides I prepared. Maybe I think that in the very beginning there's a chart shows the maybe I'm going to share the screen with you.
Yes, please. Yeah, you can share your screen.
Yeah. Can you see it now?
Oh, yeah, we can see it.
Yes.
Okay, you can see that this screen actually is located at the istt.com official website. You can see this is the figure I presented in my PowerPoint, and actually you can see in more details now. For the rehabilitation, there are different methods. I think, as I know, the not only the CIPP, but also the liner rehabilitation in general. I think there are different ways. However, CIPP could be the most popular one because we always see the CIPP in the exhibition for the ISTT Nordic event. They are different events, like a local event and also international event. I think the market for this product or this construction, I think is the most popular now. Although they I know that they are different method of curing. They could use, we could use the hot air or hot water, or you use the light, UV light, to do the curing. Okay, I think that's the. I'm wondering that I answer your first part of the question or not. But for the application, I think it depends on the liner, because when we use the CIPP to rehab the water main, and certainly it's different from the rehabilitation for the sewer pipeline, because for the water pipeline, we have to consider drinking water standard. So the chemical condition, I mean, I think the chemical, I think the standards will be more higher. There's some standard enforced by the European countries, also in the US and also Japanese, because we cannot allow the chemical from the liner to the drinking water. That's for the water main rehabilitation. For the sewer rehabilitation, I think we must consider the erosion, not only the corrosion to the metallic pipeline outside, but also we must consider corrosion and also the chemical reaction between the liner material and the sewer water, because the sewer water could be acidic, and there might be some chemical reactions between the liner material and the sewer waters. So I think that's about it. I'm wondering that I answered your question or not. Please.
Thank you. Thank you for your thorough comments. I think that will be enough. And let us begin the award ceremony.
Okay.
네, 시상식을 시작하도록 하겠습니다. 이쪽 와서. 먼저 미리 이제 버추얼로 진행을 하다 보니 상패를 전달을 하였고요. 네, 그거에 대해서 대독을 하도록 하겠습니다. KGS Award to Professor K.Jian Shu, Department of Civil Engineering, National Chungching University, Taiwan. This award is presented in recognition of your contribution and leadership in slope engineering, engineering geology, and trenchless technology in geotechnical engineering. March 16, 2022, Young-Wook Kim, Chair of Award Committee, and Moon Kyung-jung, the President of Korean Geotechnical Society. So please give big hands to the Professor Cho.
Thank you very much. Thank you very much.
Thank you. So if you have a remark, would you like to say a few words to our members?
Okay. President Chong, delegates of KGS, distinguished guests to this event. It is my pleasure to meet you on this special event. As you may know, that the KGS and the CTGS have a long history of a friendship. on the opening reception yesterday with the delegate from both sides, including President Chung and President Wang of CTGS. We had a constructive conversation and plan to work on more cooperation, and I believe you will see the development very soon. As you may know, that with the support of KGS, I have elected as the VP Asia of ISSMG, also the successor of Professor Kim. Please feel free to let me know should you have any suggestion to ISSMG for what I could do to make the society better, or especially for the Asian region. Again, thank you very much for your listening. Thank you.
Thank you. Congratulations to your the award, and also we will look forward to seeing you and working with you for the ISSMG. 이것으로 KGS 어워드 렉처는 마무리하겠습니다.